Okay, here is part two of data analysis, which involves linearization and it's what happens if the equation is not linear. So what I want you to look at right here, P versus T. And I want you to look at P and T right here. And sort of hopefully you can sort of see that none of these equations show a linear relationship. Remember, what you're looking for a linear relationship is both the exponent on the P and the exponent on the T are both 1. And hopefully you can kind of see this is not true for any of these. All right. If this is the case, what you need to do is linearize the data. All right. So let me explain what linearization means. This can be kind of confusing at first. When you do it several times, you begin to realize that actually it's like super, super simple. All right. So, but it is confusing at first. So I'll try to do a few examples. All right. And then hopefully it kind of becomes clear by the end of this video. So let me do this second equation right here so that we can sort of see P equals AT cubed. All right. And then remember, I like to kind of put a box on around the y and x variables, okay, because we're looking at P versus T, P versus T. And then if I put a box around the y variable, and then of course, why do I put the y is what I once again, just as a quick review, that's the y side because the x side is on this side because these formulas are always going to be a form of y equals mx. So that's definitely the y variable right there. So I put a box around that y variable. I can even label that with the y variable right there. But then if I put a box around this guy, right, I can clearly see that's not linear because of that guy right there, right? So this, I'm going to conclude, definitely not linear. So then the question is, what do you do? So this is going to be confusing at first, but if I look at this equation in a slightly different way, I'm going to put my box around the y variable and the x variable. So notice right there, if I put my box around that, that still looks like a good y variable. But this time, I'm just going to expand the size of my box. Do you notice that all I did right here was just make my box bigger? It still contains t, but now also contains the cube in there. So that means p versus t cubed, that is linear. So notice that I didn't really do any algebra. I didn't move anything around. I didn't like try to move letters to one side. I didn't try to take the cubed root of both sides or anything like that. All I did was literally just take, instead of my box, my x variable being this box, I decided my x variable is going to be a bigger box that includes the cube there. All right. So this t cubed is my x variable. Now, you may not fully understand right now exactly what I mean by this in terms of how this works in the context of a lab, but I want you to sort of, I'm going to have us practice this, just looking to see this x variable and see how to expand the box. All right. So let's go back to this original list. All right. And choose our y and x variables now. All right. So let me just do the first one. Well, actually, I already did the second one as an example, right? Is that my y variable could be that, but instead of t being my x variable, I'm going to include the cube in there for my x variable. All right. So here, I'm going to do p versus t cubed. All right. And in this first one, for example, okay, y variable is still there. And instead of putting my box just around the t, okay, that's not going to be a good x variable, right? Because I can see p and t are not linear there. Why? Because they're pesky, because this pesky little squared there. So all I'm going to sort of do, imagine, is that I'm going to expand what my x variable actually is. It's going to be t squared. So this is going to be p versus t squared, all right? So seeing the pattern I did for this first two, see if you guys can sort of figure out what the other three questions are going to be in terms of what the y variable and x variable are going to be, right, for all three of these. Once again, just sort of make sure that you're only looking at the t variable, the p variable and the t variable right here. Right? P variable, t variable, p variable, t variable. Right? Okay, let's sort of check your answers. Let's sort of see. This first one, y variable, and then this one's a little bit tricky. So that's not a good x variable because that t is in the denominator. So instead, you're just going to expand where your x variable is to that. So you do p versus 1 over t. This is going to be p versus the square root of t. This is going to be p. This one's a little bit tricky. Hopefully you guys got this one. See, notice that t is in the denominator and it's squared. So you're going to kind of capture both of those. All right. Now, once again, as I mentioned before, you still may not fully understand what this actually means. What the heck this actually means. So let me explain it, what this means in the context of like a lab, in what you would be doing in a lab. So let me go right here. Okay. Let me just choose. Yeah, actually, that same one we're working on right here. So the second one right here. So let's go pretend this equation once again was p equals at cubed. All right. So based on what we just said before, oh yeah, and you would have had a data table that was filled with p and t data. And based on what we just talked about before, p and t are not going to be linear. So graphing this, if you graph this right now, these data points right here, you would get something nonlinear data, right? Which is what we don't want, right? So instead, you can sort of see right here that your y variable is p and your x variable should be t cubed. So what does that mean? What that means is that you need to make a whole new data table. All right. And what this t cubed here means is that your x variable is not going to be your original times that were listed right here. You're going to take all those times and you're going to cube them. Right? So for example, if this time was like, say these times are like 1, 2, 3, 4, 5, 6, 7, or something like that, right? Then what you're going to do is you're going to take that time right here and you're going to cube it. And you'll get 1. You're going to take this, you're going to cube it, and you're going to get 8, and so on and so forth. 4 cubed is 64. 5 cubed is 125. 6 cubed is, I have literally no idea what that is. Okay, but you're going to replace you're going to make a whole new data table where instead of being 1, 2, 3, 4, 5, 6, this is going to be 1, 8, 27, 64, 125, so on and so forth, right? Now, in this other column, P, well, notice that you're not changing P. Your Y variable is still P, so all your original P's can still be here. So notice that what linearization means is you're making a whole new data table, right? And then what does that mean right now? If you graph these numbers instead of the original data table, those will be linear and they will be aligned. And that's what we mean by linearized data, right? Okay? And your graph would kind of change. I'm going to go over details about the changes in the graph, but you would change the labels of your graph too. But I'll talk about the details over that later. You notice I changed the labels in my graph. This is P, and this label right here is T cubed. All right. But right now, I want us to focus on the fact that once you know what this T cubed means, it means you got to change your data table, right? So, like for example, right here, you would have taken all your t's and just squared them. Here, like I said, you would take all your t's and you cube them. Here, you would take all your t's and 1 over them. Here, you would take all your t's and square root them. Here, you would take all your t's and like 1 over squaring them, right? So in your new data table. And for these, all your p's will remain the same, right? And you're going to graph that new data, right? So that's what the linearization step is. Now, what do you do after that? Okay, so we already just talked about these. These are your sort of new linearization, your new y and x variables. Okay. The next step is the same as before. Now that you have the y variable and the x variable, you should be clearly be able to see the slope still right there. Why? Because the slope is what's being multiplied by the x variable. Remember, t squared is my x variable, but the coefficient of that is my slope. So here I can sort of say my slope here is 3. Here I can clearly see what's being multiplied by my x variable there. So I can here say my slope is a. See if you guys can do these other three to tell me what the slope is on these three. Hopefully you got that by now. You should have seen that this slope right here is the 4a. Here the slope right here is 6x. Here the slope here is going to be 8m. And of course, what does that mean? Like, let me just use an example. Say, the slope was 6x. So say you graph something, and then you knew the slope was 6x. So after you find the line of best fit, right, and you get a number for that slope by doing, right, choosing 2 points and find this, say that slope was 5. Well, if that's the slope and that's the slope, once again, they're both equal to the slope, which means they're both equal to each other, and then you can solve that letter. So that last step is exactly the same as it was in the previous part. All right, so that's anything new. So let me show you then from beginning to end, like kind of an example scenario. Okay, right? What a lab would look like completely from beginning to end. And then this time I'm also going to show you all the little kind of detailed steps you kind of need to make sure you follow. So let's just pretend there was a lab equation. You collected, once again, I'm just going to make up some letters. V and M data. All right. And let's just say there is an equation that related V to M, and that equation was this. This I'm going to do the square root of P times M to the third. All right. So that's some crazy physics that tells you that's how V and M are related. So first thing hopefully you can sort of see is y variable, x variable, slope, right? So once again, if you want to put a box around these things, right, you can. I think it helps a lot of people to sort of see y variable, x variable. That's what we just talked about, right? See that linearization? And once again, how did I know I was supposed to look at the m for the linearization? Well, because m was related to the x variable. So I don't want to look at the p to find the x variable. I'll look at the m. But I can't just put a box on the m. That would not be linear. So I have to expand my box to include the cubed on the m. That's my x variable. So right here, this is y variable, x variable. And then notice what's being multiplied by my x variable. There, slope. So notice that means I can come right down here, right here. I already know right away. That's slope right there, square root of p. All right. Let me keep on going right here. Notice what this means. I need to make a whole new data table. We're going to take all my m's and cube them. So all of these numbers right there, I'm going to cube them over here. Right? All those v's, I can rewrite here if I want. And then it's this new data table that I'm going to graph down here. So I'm going to label right here. Okay. Notice there's a subtle thing right here, which is the changing that label there, which I'm going to talk about later in a bit. But that label is not m anymore because I plotted these. So that's going to be m cubed. All right. So I'm going to erase that circle for now. It's sort of distracting. But if I plot this new data table, I will kind of should get a line of dots. The rest of the steps are sort of the same. Oh yeah, by the way, this graph title I will label y variable versus x variable, just like before. Notice my x variable is not m anymore, it's m cubed, so my title changes here. Okay. Anyways, dots, line of best fit. Find the slope of that line by taking 2 points, right? Look for 2 grid points. There maybe, and there. Rise over run. Show your slope calculation, right? Whatever this minus that over this minus that, whatever you're doing to find the slope calculation. Let's just pretend I got 5. All right, so I just made that up out of the gate. All right, last step is exactly the same. All right, if 5 is a slope and square root of p is a slope, that means I know the square root of p is equal to 5, and then I can solve for p, and then I know that p is 25. And this is how every lab is going to be done. And this is the linearization step. Right? Now, one thing, a couple of details I want to point out about these labels. Notice the labels on my axis have changed. The other steps are the same. You kind of choose your scale appropriately, just like before, right? But one critical difference right here is these units. These units, you need to put those units in. And so these units, like for example, let's say V happened to be velocity. So those units might probably be meters per second. So you might put meters per second there. And then say M was mass. So M might be kilograms. Here's a common mistake right here. Notice that these units are wrong because those are the units of M. But this is M cubed. So that means these units need to be kilograms cubed. In other words, the units change with the exact same way the variable changed. So you need to kind of reflect both of those changes right here. Right? But this is the general steps that you're going to be doing for every single lab. So every single lab is going to follow this exact same pattern all year. Okay? So, all right, that's the end of this video. Hope that helps.